Okay, so let's take a look at this example where we're given this function y squared plus x squared y plus x squared minus 2y, and what we want to do is to find all the critical points of this function and classify each of them as either local minimum, local maximum, or saddle point using the second derivative test. Okay, so to repeat the procedure, first we need to find the critical points. So the function is a polynomial, and so polynomials are defined everywhere. So the critical points are where the first order partial derivatives are equal to 0. So the first step is to find all the critical points. And the way we do that is to calculate the partial derivatives and set equal to 0. So set the first partial derivative with respect to x equals 0, and the partial derivative with respect to y equals 0, and then solve for all points x, y. So the resulting equations okay, so so that's what we need to do, right? So we need the first order partial derivatives, so let's write them down. So what's the partial derivative with respect to x? So we're treating y as a constant, right? So derivative constant is 0, so this term goes away. Here y is a coefficient, so the derivative doesn't affect y, and then the derivative of x squared would be 2x, so you get 2xy. And then here the derivative of x squared again is 2x, and then here this only contains y, so a derivative of a constant is equal to 0. Okay, so this is the partial derivative with respect to x, and I set it equal to 0. Now the partial derivative with respect to y, so the derivative of y squared would be 2y. Here x squared I think of as a constant coefficient, so it doesn't affect the x squared. Derivative of y is just 1, so multiplying by 1 doesn't do anything, so it's just x squared here. And then here this we're considering x as a constant, so the derivative of this goes away. And then finally the derivative of minus 2y is just minus 2. Okay, and then I set it equal to 0. Okay, so now essentially I have these two equations, so this thing equal to 0 and also this thing equal to 0, and I need to solve both equations for x and y. So in this case both equations involve x and y, and they're also nonlinear equations, so sometimes these equations can be difficult to solve. So the strategy we're going to do here is to try to solve one of the variables, right? So between the two equations, you want to find the easiest variable to solve for, right? So in this case, it's going to be the variable y coming from this equation. So again, the strategy here is going to be to solve this for y. And then we're going to plug in the result into the first equation. Okay, so so again, I mean, typically the equations, there's no real pattern to trying to solve these, right? So you have to look at your two equations and figure out what the best course of action is. Again, in this case, it's going to be to solve this equation for y in terms of x and then plug it into the first equation. So what do I have? I have 2y, and I'm going to subtract these two terms. So you get 2 minus x squared, and then dividing by 2, I get y is equal to 1 minus x squared over 2. Right, so dividing by 2, and then, okay, so now, so let's highlight what's going on. So I'm going to take this equation and I'm going to plug it in to the first equation. So what's going to happen is that the resulting equation will now only contain x, and then I'll be able to solve for the values. Okay, so let's write it out. So we have 2x times y, which is now this thing, right? So 1 minus x squared over 2 plus 2x is equal to 0. Right, so just writing this out with the y plugged in. Okay, so now let's simplify this, right? So 2x times 1 is just 2x, and then minus 2 divided by 2 cancels out, so you're left with x times x squared, which is x cubed, and then plus 2x equals 0. Okay, so 2x plus 2x gives you 4x. Okay, so now we see that my equation only involves x. So now I try to solve this for x. So let's factor out one of these x's. So you're left with 4 minus x squared is equal to 0. And then separating the factors, you get x equals 0. So that's that's one of my x values. And so I'm going to eventually need more space, so let me add an extra page after this. In any case, so separating the factors, I get x equals 0, and 4 minus x squared equals 0. So again, trying to solve this, you get x squared is equal to 4, or x, so taking the square root, you get x is equal to plus or minus 2. Okay, so I have 3 different x values. Right, so x equals 0, x equals positive 2, and x equals negative 2. So I'm not quite done yet, right, because the critical points are ordered pairs x and y, right? So I only have the x values, and so now I need the y values. So to get the y values, I just plug the x values back into the other equations. So to get the y values, plug the x values into here, right? So so let's do that. When x equals 0, what do you have? Y is equal to 1 minus 0 squared over 2, and so this is just equal to 1, and so here y equals 1, so the point is going to be 0 comma 1. Okay, so that's my first critical point, and when x is equal to positive 2, again just calculating, y equals 1 minus 2 squared over 2, so I'm plugging all of the x values back into this equation. So what is this? 2 squared is 4, 4 divided by 2 is 2, and then 1 minus 2 is negative 1. Okay, so I get the coordinates 2 comma negative 1. And then finally, when x is negative 2, you get y is equal to 1 minus negative 2 squared over 2. So essentially this is the same calculation, so this comes out to negative 1. So I get the point negative 2 comma negative 1. Okay, so just squeezing it into the corner here, but these are all the these are the critical points. Okay, so in this example, my function has 3 critical points, and so now what we need to do is to classify the critical points using the second derivative test. And so that's going to be involve calculating the discriminant. So let's just copy down the discriminant here. So it's the it's fxx times fyy minus fxy squared. Okay, so so since the discriminant involves all the second order partial derivatives, first we need to find the second order partial derivatives, right? So the second partial with respect to x, so I have to take this function and then take the partial with respect to x again. So what do I get? I get, so this term is 2y, and then this term is plus 2. So you get 2y plus 2. And then I need the second order partial derivative with respect to y. So I have to take this one and take the partial with respect to y again. So these two terms go away, and I'm just left with 2. And then I also need the mixed partial, fxy. So I have to go back to the first one here and then take the partial with respect to y. So this term goes away, and I'm left with 2x from this term. Okay, so that's all of the second order partial derivatives. Okay, so I mean, in this particular example, the second order partials aren't too complicated. So what you can do is to carry out this calculation here in terms of x and y, and then plug in the coordinates for the critical points at the end. However, if your second order partial derivatives have more complicated expressions, a better way to do it might be to do the following. So I'm going to separately calculate each of these for each of the critical points, and then organize the values according to the in a table in the following way, right? So I have my 3 critical points, right? So let's list them here. It's 0, 1, and then 2, comma, negative 1, and then negative 2, comma, negative 1. So those are my three critical points. So let's list them here. And then I'm going to calculate the second order partial derivatives separately for each of the 3 critical points. So again, it's not completely necessary in this particular example because the expressions are not too complicated. But for a more complicated function, this will help you organize all of the calculations. Okay, so for each of these, I'm just plugging in the x and the y values, right? So so let's just make a notation here, right? So this is A and this is B. Right, this is A, this is B, this is A, this is B. right? So if I plug each of them into the corresponding second order partial, right? So here I just need the y coordinate, so 2 times 1 plus 2, so this is equal to 4. This one would be 2 times -1, so you get -2 plus 2, which is 0. And this one again would be 2 times -1, which is -2 plus 2, which is equal to 0. Okay, so now what about the fyy? So here it's constant, so always equal to 2. So you don't have to calculate anything. And then here, for this one, I need to plug in the x coordinate. So if I plug in 0, this is 0. If I plug in 2, 2 times 2 is 4. And if I plug in -2, 2 times -2 is equal to -4. Okay, so so having plugged in, having calculated all of these, now I can just put it together for the discriminant, right? So so let's calculate the discriminant for each of these. So for when you have 0, 1, right? So the discriminant formula, again, I have at the top here. Right, so let me just write it down again. So you can see how the calculation is going to proceed, right? So it's fxx times fyy minus fxy squared. So basically it's just this times this minus this squared. So d of 0, 1, right? So it's this times this minus this number squared. So this, I get 8. The discriminant for the next one is equal to this times this minus this squared. So 0 times 2 minus 4 squared is equal to, so 0 minus 16, so -16. And then finally, the last one. So it'll be 0 times 2 minus a -4 squared. So this is positive 16, but then because of this minus, it's going to be minus 16 again. Okay, so those are each of the discriminants. So what's important is whether it's positive or negative, right? So this one is positive, this one is negative, this one is negative. Okay, so so what does that mean? So going back to the second derivative test, when the discriminant is negative, then you have a saddle point. So that means that these two are saddle points. So at 2, -1, and then this one is also a saddle point at -2, -1. Okay, so those are the those two critical points. And what about this one? So when the discriminant is positive, when the discriminant is positive, you have to look at the second partial with respect to x and look at that, whether that is positive or negative. So basically concave up or concave down, right? So in this case, for this critical point, the second partial with respect to x was positive, right? So here, fxx of 0, 1 was positive. So what does that mean? Discriminant is positive, and this is also positive. So concave up shape means you have a local minimum, right? So it's essentially this shape here. Okay, so we have a local minimum at the point 0, 1. Okay, so we've classified all of the 3 critical points. Okay, so to give us an idea of sort of what's going on in this function. So let's try to graph the function and actually see where these 3 points are occurring. So so I'm going to go over to this GeoGebra website to use the 3D calculator, right? So first I'm going to enter in my function, so f of x, y. So what was the function again? So y squared plus x squared y plus x squared minus 2y. What's going on here? That's not what I want. Delete everything. So f of xy is equal to, what was it? Y squared plus x squared y plus x squared minus 2y plus x squared minus 2y okay, so so it's drawing the graph here. So this is what it looks like. So you can see that there's a local minimum here, and this is going to be one of the saddle points. Okay, so but let's actually try to locate the points exactly, right? So what were the critical points I calculated? The first one was 0, 1. So let's locate them on the graph, right? So the x coordinate was 0, the y coordinate is 1, but I also need the z coordinate. The z coordinate is just the function value, so f of 0, 1. So here, so this is labeled the point A, and you can see that in the graph, the point A is located here, which is exactly where the local minimum occurs. Right, so that's exactly what we identified as the local minimum. Okay, so now let's do the two saddle points. So I want 2, negative 1. So let's just have the function calculate the z value. So 2, negative 1. And then the other one was negative 2, negative 1. And let's have the computer calculate the function value. Okay, so at 2, negative 1, and then at negative 2, negative 1. So we should have 2 critical points, and when we rotate the graph, you can see the point B is located here at this critical point, so that at this saddle point, and the point C is located here at this saddle point. Okay, so so here it can be useful to try to visualize the graph using this website, so that we can confirm, make sure we did all the calculations correctly in identifying these critical points. Okay, so that's how we use the second derivative test.